Esme is going to be talking to us today about some seismicity associated with dyke propagation during the recent volcanism in the Reykjanes Peninsula, Iceland. So Esme, whenever you're ready, the floor is yours.
Thanks, Sophie. So hopefully you can see my screen and not my notes. Good. Great. Well, afternoon. I'm Esme. Thank you very much for having me as part of this International Women's Day webinar. I'm like Sophie said, a volcano seismologist at the University of Cambridge. I'm in the final year of my PhD, supervised by Nick Rawlinson, Bob White and Tom Winder, and I've got a long list of international colleagues too. So this talk is about my work on seismicity associated with the 2021 dyke intrusion at Fagradalsfjall, Iceland, and what was controlling the faulting. So it's quite a short talk, so I've had to leave out a bit of the nuance, but I'm going to quickly introduce Iceland and the Reykjanes Peninsula, where all this recent volcanic activity has been occurring, before describing some of my results with some quick methods kind of mixed in, and discussing what was controlling the faulting associated with this first dyke intrusion. So I think my pointer's a bit off because I'm in presenter view and showing you the slideshow, but I'll try and use it anyway. So Iceland is unique, being the coincidence of a mantle plume and the mid-Atlantic ridge, which has given rise to this island with elevated volcanic and seismic activity. And the Reykjanes Peninsula, which is here in the southwest of Iceland, is a particularly interesting part because it's where the mid-Atlantic ridge comes ashore in a highly oblique rift zone, meaning that the direction of plate spreading is at a high angle to the plate boundary zone, which makes things quite complicated. So this rifting is accommodated differently in different parts of the peninsula and throughout different time periods, but in the vicinity of Fagradalsfjall, which is here, it's mostly by bookshelf faulting on north-south-ish strike-slip faults, which will be important later on, and also lately accommodated through magmatism. The Reykjanes has a rich volcanic history, but was dormant for over 700 years until 2021, which was conveniently the year that I started my PhD. And there have now been 10 eruptions, starting with 3 in the Fagradalsfjall volcanic system, and continuing today with 7 so far in the neighbouring Eldvurp-Svartsengi system. And the first dyke intrusion at Fagradalsfjall in February to March 2021 lasted 3 weeks and was followed by 6 months of eruption. Sneak peek at some results to help my intro here. So this movie is going to show my earthquake catalogue for the 3 weeks of dyke intrusion in map view through time, with the colour bar showing most recent earthquakes. It was marked by over 80,000 micro-earthquakes, triggered as the melt moved through the crust, and they ranged in magnitude from -0.3 up to 5.8. Hopefully you can see the video moving. The dyke originated around here, propagating firstly northeastwards and then strangely turns back on itself and overshoots its starting position to the southwest before eventually turning back once again, with melt eventually surfacing here. I have no idea where my pointer is, where you can see it, but there's some stars under there that should show its location of the eruptive vents. So its eventual path was around 9.5 kilometres long, with 2 main segments. So one more north-south striking southern one and a slightly clockwise rotated northern one. And this seismicity provides us with insight into the relationship between volcanic processes, pre-existing structures, and the regional tectonic setting. Which leads me to define my research question concerning the controls on faulting associated with the dyke intrusion. So there are 2 main possibilities. So firstly, option 1, if a dyke intrudes into fresh, non-fractured country rock, theoretical models predict that 2 sets of conjugate fractures will be formed at the dyke tip, with right lateral slip anti-clockwise and left lateral slip clockwise. And this has been observed in nature, such as at the 2000 dyke intrusion at Miyakojima in Japan, where the stress field imposed by the dyke was strong enough to change the background seismicity. And we'll call this scenario classical dyke tip fracture. The second scenario can arise when an intrusion occurs in a region with strong regional fabric and many pre-existing structures, which may influence how and where the faulting occurs. So this was seen at the Vardabunga-Holloran dyke intrusion in 2014 in Iceland's northern volcanic zone. And there are some nuances to this case, but the conclusion was that the orientation of faulting stayed the same even when the dyke changed strike, like it does here. And as the strong rift fabric exerted control, conjugate sets of faults ahead of the dyke tip were not observed. So my question then is whether the faulting associated with the 2021 Fagradalsfjall dyke fits either of these cases. Do we see classical dyke tip fracture, or is the faulting controlled by the extensive network of pre-existing structures? Now, this question can best be answered with a detailed study of seismicity recorded by an exceptionally dense local seismic network, which is lucky because that's what I have access to. The Fagradalsfjall dyke, roughly here in red, intruded right through the middle of this amazing network, which is jointly operated by my group and these institutions here in the Key. The network also provides great azimuthal coverage, which is important for my analysis too. And this is really just an excuse to share some fieldwork photos, but in the spirit of International Women's Day and Women in the Field, I've been really lucky to have been part of deploying and servicing the network over the years. Most of the time is hard work, but not all of the time. So now that the scene is set, let's look at some results. So to answer the question of what controls the dyke-related faulting requires 3 key pieces of information. So I need to accurately determine the strike of the dyke, the strike of the individual fault planes and their sense of slip, and compare both of these to the strike of pre-existing structures. And these relationships should then help us to understand the controls. So for the first of these, the strike of the dyke, we can use the location of the seismicity as a proxy, which agrees well with other published estimates for the dyke location from, for example, INSAR modelling. So I created a catalogue of the seismicity using this program Quake Migrate, which uses migration-based techniques on raw waveform data, and I created a catalogue of 80,000 automatic earthquake origin times and hypercenter locations. I then broke this huge catalogue down into subsets to reduce computational costs for subsequent analysis, choosing then to define 5 swarms of seismicity, which you can see here in colour on this map, which covered the length of the dyke, and which were occurring during periods where the dyke was propagating quickly along strike. So nicely visible on this timeline of seismicity projected as distance along strike of this line of cross-section from the map on the previous slide. And these swarms also happen to be when most of the large magnitude earthquakes are occurring. So I then relatively relocated the hypercenters, which is processed to refine the earthquake locations. So with a program called GrowClust, I cross-correlated waveform data is used to compute similarity coefficients for pairs of earthquakes, and events are clustered according to this similarity, with events within the cluster then relocated relative to one another. So I then used linear regression on the hypercenters in these relatively relocated swarms to fit a line and identify the strike of the dyke in each section. So here you can see those relatively relocated swarms in colour against the background of the more diffuse automatic catalogue in black, with the lines of best fit on top. And so now we can start to see this 2-segment geometry coming out a bit better, which has been reported by other studies too, where this south half of the dyke has a more north-south strike than the northern half, which is rotated clockwise. Next, I need to know about the individual fault planes. So I chose a smaller handful of events again from these swarm subsets to analyse manually using P and S wave arrival picking. So from the raw waveforms in this program Snuffler, I can apply filtering to remove noise, and then I mark the P and the S wave arrival times and assign a first motion up or down polarity to the P wave, like in this up example here. And you can then invert for a fault plane solution using a program called MTFit. Just to remind you what a fault plane solution looks like, so this is an example from Swarm B. So each polarity pick at each station is represented in lower hemisphere projection with a red circle for an up first motion or a blue triangle for down. And then MTFit computes a range of possible solutions with the most probable nodal planes highlighted in blue. And we then represent these as beach balls with shaded compressional quadrants where first motions are up and white dilatational quadrants where first motions are down. With this example showing a right lateral strike slip mechanism with the more north-south plane interpreted as the fault plane from regional context. And this also shows how the amazing azimuthal coverage of our seismic network helps to constrain those solutions. So I have 97 fault plane solutions, and 96 of these show right lateral strike slip faulting on roughly north-south striking fault planes. If we look at these circular histograms of the fault plane strikes versus the dyke strike, we can pull out 2 main things. Zooming in here, firstly, the fault plane strikes are offset anti-clockwise from the dyke strike, which is the red dotted line here. And secondly, this change in strike, rotating slightly from south to north, also occurs in the fault planes. And so far, this is just what we expect according to Moore-Coulomb and Andersonian models of faulting, where dyke intrusions will propagate along the direction of maximum horizontal stress, and failure occurs on planes around 30 to 35 degrees offset from that. So on the Reykjanes Peninsula, this corresponds to northeast-southwest trending dykes and failure on north-south striking planes. And local variation in this is probably causing this two-segment rotation effect. The final thing then is to quantify the fracture orientations. So I used a couple of data sets of map fractures from other studies, which were compiled through a mixture of field mapping and INSAR, and analysed those in the vicinity of the dyke within these coloured boxes. And then I produced some length-weighted circular histograms of these fracture strikes. Once again, we see this clockwise shift in north-south-ish fractures from south to north, and there's also a bimodal distribution of strikes in the southern section. And this results figure from my paper that's currently in review with JGR shows everything together. So now I have these three things, we can start to see whether the observations fit either our two initial hypotheses, so classical dyke tip fracture or slip occurring on pre-existing structures. For the purpose of summarising, on the next slide, I'll stop talking about this in the context of swarms, and I'll group the analysis into just the north and the south segments based on this red line on the map here. So with the orientations summarised here, split north-south, like I said, with the three key pieces of information we set out to obtain and compare, we have the dyke strike, we have the fault plane strikes, and the fracture strikes. If we zoom into this all data column, this shows everything superimposed. So we can see that both the fault planes, which are in black, and the fractures in blue are offset from the dyke strike in red in both the south and the north. And we also see within uncertainty, which is the transparent regions behind, that the fault plane strikes align well with the fractures in the northern segment and with the north-south population of fractures in the south. And in the south, we have the secondary population of fractures I mentioned earlier, but we have no fault planes which align with these. So starting to sum up then, what my observations show is a lack of evidence towards the theory of classical dyke tip fracture. So this cartoon, if we consider as an example the northeast tip of the dyke and the southwest tip of the dyke, it shows what a conjugate set of fault planes would look like if you had left lateral slip in red orientated clockwise of the propagating dyke tip and right lateral slip in blue orientated anti-clockwise. But the only nodal planes I observe are those in the black outlines here, which you can see only fit with the right lateral anti-clockwise blue ones, so no conjugate sets. Instead, therefore, if we only see right lateral slip anti-clockwise of the dyke tip on planes which align well with the pervasive network of pre-existing structures, this is in favour of the theory that pre-existing structures exert primary control over the faulting. So this summary cartoon shows our suggested model. So in this region with pervasive pre-existing structures and rift-related stress regime, the dyke, which is this red shape, propagates, exerting stresses on the primed pre-existing structures surrounding its tip, upon which slip occurs, and those structures are exerting the primary control over the orientation of dyke-related faulting. And I think I will leave it there now, and I will just let this video of my relative relocations for the whole dyke catalogue play, including this time a north-south cross-section on the right. So my future work will be to expand this to a detailed study of the whole dyke intrusion period, not just within these swarms, and to also compare the dyke to a horizontal sill intrusion, which occurred in the neighbouring Eldverp-Svartsengi volcanic system in 2022, to see if a different geometry of intrusion has an effect on the resulting seismicity. And thanks very much for listening.
Thank you so much, Esme. That was great. I really like these animations, and the videos are awesome. And there's no questions in the Q&A just yet, so I can at least kick us off with one. And if you do have questions, please pop them in the Q&A. So these structures are really cool that you've shown the segmented movement. Have you noticed any distinct patterns in terms of the magnitudes as well as in terms of the locations of the events?
Yeah, I've had a look actually. Plotted everything I could think of plotting with magnitudes through time, magnitudes laterally, magnitudes in depth, which is not something I talked about a lot with the depth this time, and basically no patterns yet observed. Something I've also tried to look for is whether there are these sort of aftershock patterns like you'd expect with kind of tectonic earthquakes, and that's really difficult to see as well. And I don't know whether it's just because the catalogue is so intense that it's just kind of happening all over the place. But I'm hoping these relative relocations for the whole dyke might help to see that in the future.
No, that's cool. We've had a few questions come through. One question, so are there any observations for lateral motion component on the dyke itself?
Lateral component motion. What does that mean?
Motion component. I don't know. Can you see the Q&A? I'm just...
No,
don't worry. It's okay.
Oh, no, I can. It's different.
Are there any observations? I want to say any surface expression. Maybe it refers to surface.
Oh, yeah. So yes, we do have surface ruptures in some places. So one of the best examples was actually near the town of Grindavik, which is the town that you might have heard on the news, which has all had to be evacuated now with the latest eruptions. And there's this beautiful kind of, just like you see in your lectures, like a road marking, like the lines down the middle of the road have been perfectly offset in right lateral north-south strike slip. A lot of it at the time at the surface is kind of just graben structures instead. But yeah, there are one or two really nice examples.
That's okay. The question, they've actually clarified, sorry. So that was my fault. I misinterpreted. So is there right lateral slip also along the dyke or only pure opening?
Oh, right. Yeah. So this, if you see actually in my relative relocations here, we're starting to see something which will hopefully help us answer this question. At the moment, I've done some full moment tensor inversions. All the moment tensors that I showed at the moment were double couple. I have looked at full moment tensor, and there is not a big volumetric component to any of it. In the relative relocations as well, you can just about see that we've got all these kind of north-south structures, kind of a lot of it's off dyke as well. So I think a lot of the seismicity doesn't show a volumetric component, and it's just triggering slip on these north-south faults. Yeah, hopefully I answered that correctly that time.
Got time just for one more question and move on. So one question, what is responsible for such a dense set of pre-existing fractures that are accommodating the slip?
Yeah, so like I said, I mean, there's been a long history of tectonics and volcanism on the peninsula, just not recently so much. So I think it's all just, yeah, this across the peninsula in the far northwest and the far southeast, I think there's kind of big normal faults. But yeah, in this kind of plate boundary zone that I showed before, this whole oblique rift is accommodated, we think, over this pervasive network of like bookshelf faulting, like is what we say when you imagine like books on a shelf, and if you tilt them, you get this sort of rotational but also extensional kind of thing happening. And we think just over thousands of years, that's how the accommodation related to the rift has been accommodated. Extension. Yes.
That's great. Thank you. That analogy of the bookshelf is it's a very helpful visual. There's a few more questions in the chat, in the Q&A, but we do need to move on kind of in the interest of time. So I think, Esme, your contact details are available. So if you have any more questions, obviously, please get in touch with Esme. We have time for one more speaker. We're coming to our last speaker, which is Dr. Camila Novoa-Lizama, a COMET postdoc at the University of Leeds. Staying with Geodesy and INSAR, but in a different applications. We're looking at volcanic environments, 2016 eruption of Nevados to Chillán complex in southern Chile. Hopefully, technical difficulties aside, we're ready to go. So Camila, if you want to share your screen and you have
the rest. If it works.
Yeah, that looks beautiful.
Perfect. So can I make it this smaller? Yeah, that's perfect. Oh, I think it's not from the beginning. Oh, sorry about that. Yeah, so the presentation I'm showing to you today is part of it's a paper that it has been published last month, and it has been a collaboration between researchers from France, from Chile, and from Leeds. So Nevados de Chillán is one of the more than 100 volcanoes active in the south of Chile. And it belongs to the southern volcanic zone. That the volcanismo is its origin is on the subduction in which the Nazca plate is subducting the South American plate. In this volcano, the eruption started 40,000 years ago, and it has been concentrated in two areas in Cerro Blanco complex that you can see here, all the eruptive products in blue, that they are more mafic, basaltics, andesitics you can find here. And over the last 100 years, all the products has been originated in Las Termas subcomplex, where the composition is more dacitic. This volcanic complex is 16 kilometers long and is oriented northwest-southeast. What we know, what is happening underneath this volcano, different studies from geophysics and also from petrology, converging also with field-based evidence, indicate that underneath this volcano there is a vertical compositional zonation, so it elongates for over 20 kilometers depth. And it's very interesting because it's composed by two main reservoirs, one more basaltic, a deeper one, and a shallower one, more evolved, that is dacitic. And it has been postulated that all the last eruptions in this volcanic complex has been with the same mechanism, in which a mafic magma from the deep reservoir reach the shallow reservoir and produce these eruptions dacitic. So here in this study, we were trying to see if such a mechanism can explain the activity that we have in this volcano over the last eruption. So let's see the activity. So this eruption starts in January 2016, and it starts with a strong explosion, and we have explosion activity for, well, this activity extended for 6 years. It finished in January 2023. And it started with 8 months of explosive activity in which they measure gas, and you can see juveniles for the first months, and then no more juveniles. So it has been an activity phreatic that then evolved to phreatomagmatic. And at the end of 2017, it started the mafic activity, in which we can see lava domes at the surface. And it's very interesting in terms of geodesy, because over these first 3 years, despite we have a lot of eruption activity at the surface, we don't see, this is GPS over the time, we don't see any deformation at all. Here is an interferogram that you can see the strong deformation at the Muyo. And in Nevados de Chillán until December 2017, we didn't see any deformation. Then this activity evolved to more mafic, and finally we see a lot of lava flows at the surface. Here I'm showing to you 4, but they are like 7 afterwards. And it's very interesting because as we have lava at the surface, these lava flows are correlated with an uplift that started in August 2019 that you can see here. And here finally we can see an uplift event in the interferograms, also has been captured by this GPS. So this study has studied this uplift until the beginning of 2020. Then Astor and collaborator continued to study this uplift. They saw like 12 centimeters of uplift, and they modeled this uplift as a reservoir at 6 kilometers depth and a spheroid, and then they can well explain the deformation. And this was what we know until then, but this eruption continued until 2023. So here what we have done, we prolong the time series to see how this uplift continue over time. And also we are trying to understand the dynamic underneath this volcano. So similar to the other studies, we observed a clear uplift starting in August 2019. And here you can see we have 5 GPS stations, 4 at the volcanic edifice and 1 far away, 10 kilometers away from the volcanic edifice. And we were studying with Sentinel-1 and ALOS-2. we see clearly the deformation is centered in the same place where all the eruptions occur over the last 100 years. We saw, similar to other studies, that the inflation was almost linear, but we observed that for the next 2 years, it started to decrease exponentially. So, and also we observe a little subsidence just before this uplift. So this is very interesting. This is a time series of GPS of the GPS station more close to the maximum deformation here, and this one is Tran, is this station 10 kilometers away. We see that during the first 3 years on Tran, we don't see any deformation, but in FRC, we see a little subsidence occurring previously to the uplift, and which is correlated with the construction and destructions of lava domes that we are seeing at the surface of this volcano. Then this uplift event, we see that it has a strong rate, a high rate that is correlated with a high quantity of seismicity. Here you see the quantity of LP by day. And then the seismicity decrease again, but we see that the uplift continue to go, but at this time with a decrease rate. So, and this is where the lava flows were observed at the surface. So here we took the 5 GPS stations and we did a principal component analysis, and we show with the first component we can explain the 95% of the deformation. And here you can see that these 4 stations are the one more close to the volcanic edifice. We can explain them very well with the first component that here is in red. Nevertheless, we observed that at Tran, that is 10 kilometers away of the volcanic edifice, we couldn't explain well the temporal evolution, as at the beginning, in Tran, we don't see a high rate uplift. So then we take this first component and we fit our different temporal evolution with a basic exponential function. And we see with this function changing A and B, we can clearly fit the deformation in this 4 GPS GPS station. Nevertheless, it was impossible to fit Tran with the same coefficient tau, that basically it shows you that the temporal evolution it has been produced by the same source in the volcanic edifice, but apparently this tau should be very different at Tran, which makes us to think that probably another source was contributing to the ground displacement that we were observing. So with that in mind, and taking into account the different studies that indicate that there are 2 sources interacting during eruptions, here we try to construct a model in which we are trying to reproduce the temporal variation in these 5 GPS stations, relating them to 2 sources that they are evolving with an input of mass here, and then basically the dynamics between these 2 sources will dominate how much pressure these 2 sources are having, and this overpressure then will be related to the vertical displacement that we are observing in this 5 station. So basically here we develop an analytical solution for the dynamic between these two reservoirs. Here the input is a mass input. With that, we can obtain the accounting this is a constant mass input. Then we can recreate the overpressure in the shallow reservoir and also in the deep reservoir. And then with that, we relate the surface displacement that we are observing at the surface. Here, it's important to notice that the overpressures in this source will change depending on the geometry of the source. So in order to take into account the topography in this area, and we couple this analytical model with DefBulk, which is a 3D boundary element method in which we can enter basically INSAR data, GPS data, and the topography, and therefore we can search for the best source that can recreate the surface displacement that we observe. So we use DefBulk to try to constrain what is the geometry associated to this source. We take the cumulative displacement observed in the area, and that it has been shown here by ALOS 2. And here you see the observation. We make an inversion with a lot of different models. And at the end, we found that the shallow reservoir can well reproduce the surface displacement with a source at 6 kilometers depth, oriented northwest-southeast. And then we found also the deep reservoir. We found that with a seal-like source, we can well reproduce the displacement that we have. This is the cumulated displacement. Like that, we have the geometry of the source. And then this geometry, we put this geometry in, with that geometry, we calculate the overpressure associated to the displacement, and therefore, then we resolve for the overpressure or the volume change in both sources. And with that, we show that now we can well explain the temporal evolution in the sources close to the volcanic edifice, but also we can well explain the temporal evolution at Trand, that is 10 kilometers away. And we think that the big difference between the temporal evolution of these two sources is related to the temporal evolution of the pressure under the deeper source. So basically, we found that with a constant mass input of 0.015 kilometers cubed by year, this mass input will promote a decrease of volume in this reservoir at depth that then will increment again, and this mass balance will promote the continuous exponential increase in the shallow source. So basically, what we are saying is at the beginning of when we have like this high rate uplift, the material entering the reservoir is lower than the flow going to the shallow reservoir is higher than the material entering here, so it promotes imbalance in this reservoir. So the flow here is higher than the material, so it will promote the pressure will decrease in this reservoir. So we think that this is related that when we have an input of magma, it will come with a lot of gases, that it will promote the rapid ascent of these gases connecting this shallow reservoir. So, and then after a while, the flow of magma between the deeper and the shallow reservoir will decrease, and therefore the volume of magma arriving will be higher than the one going to the shallow reservoir, and therefore the deeper reservoir will start to increment their pressure. And with that, it will explain the main dynamic in this during this uplift event. Then what we think it happened the first 3 years is that there was a small intrusion at this volcano that was not enough to be captured by INSAR or GPS. And this, we think it was a very short intrusion, and then the magma added to this shallow reservoir start to be transported to the volcanic edifice. And during this transport, it will decrease the pressure in the shallow reservoir, and it's for that we will see this subsidence located in the volcanic edifice. And then, well, we think that this uplift, it's promoted by a new intrusion, that this fast ascent at the beginning will correlate with the high seismicity observed. This first 6 months, and then the decrease in the uplift in the rate will be related to the ascent of magma without, more easily after all the gases has been transferred to the surface. So in general, we have studied the 6-year eruption at Nevados de Chillán, showing these two different patterns. During the explosive phase, we saw minimal deformation, and then when the lava flows were there, we saw a huge uplift event. We think that this uplift event, it was related to the dynamic between these two reservoirs. And well, this model can be used for other situations, for other uplift, and it accounts the topography and the different source geometries. And voilà, that's all. Thank you.
Thank you so much, Camila. That was brilliant. We're running quite close to 5 o'clock, so we have a couple of questions in the chat. We might not have too many. So the first question is, does the model account for extrusion of lavas in the mass balance?
That's a good question. We didn't include it because we didn't observe a clear subsidence first at the surface to constrain the cool out at the end. And also, as we have a big inflation, we were thinking the only way in which we have a big inflation is what the material extruding is a lot lower than the material entering to the shallow reservoir. But it's something that we would like to do in the future.
Okay, no, that's interesting. I think probably in the interest of time, we'll just have this one last question. So did you try to include the pipe connecting the shallow reservoir to the surface in your model?
Yeah, well, it's exactly the same question. We make a huge assumption is that the material going out of the surface, it was very small related to the material entering into the shallow reservoir, so we didn't include it. But in the future, we would like to include it because apparently there are some measurements of the volume of material at the surface, either the part of explosive or the effusive. So if we can have the volume of the eruptive products over time, we can include the quote. So yeah.
No, that makes sense. Okay, I think in the interest of time, we will wrap up there. There are a couple of questions in the chat, in the Q&A, sorry, that perhaps maybe if you feel obliged, you can reply to by text. But can we thank our speakers once again? Thank you all for taking the time to present and share with the group today. Our next COMET webinar in April, the details will be with you very soon. And the recording for this session will be up on YouTube again very soon, by the end of the week, next week sometime. Thank you very much for joining us today, and see you next time.